folks who asked a question about these margins of error and where they came from, I think it's time to start attacking that right now. I think it's time to start attacking that right now, because it really, honestly, we did fictionally make these things up. I don't know which one is correct, because I can't do arithmetic in my head, especially the arithmetic we have to do for this. So what we're going to do is, we're going to take a trip down memory lane. Now, don't memorize any of this. This is simply placed up here to show you where we're coming from and where we need to be. So I'm going to bring up some of this stuff from 243, which essentially is this right here. And I'm going to show you how that ties to where we need to be now, which is down here. So first off, you learned this in 243 eons ago or months ago or years ago, whenever it was. When you have the binomial distribution, why would I mention the binomial distribution right now? I'm going to bring that back up. Why the hell, Allie, why?
Because there's only two outcomes, heads or tails.
And if you spin a coin, you're going to get heads, you're going to get tails. Some would argue you can get an edge or some other deviant case, but it happens so infrequently, i.e. it's never happened before, I'm going to assume it's not a case. Did I tell you, speaking of which, remember the chicken experiment we did in 243? Did I tell you a student emailed me and said there's actually a chance that a chicken can be born with both genders? And my math was wrong because of that? Did I tell you about that? No. Yeah, they did. They said, and I Googled it, and it's true. 1 in 10,000 chicks, approximately, are born with both sets of genders. So I reran the distribution as a trinomial, and guess what the difference is between my answer and theirs? 0.04%. Yeah, it happens so rarely that it's not even worth talking about in the grand scheme of things. I bring this up because technically there could be an edge result on the coins, yeah? But it's never happened before, so we can go ahead and ignore it because it probably wouldn't have that much of effect anyway. Fair enough? So if you can make it be binomial, then we can launch into this. So in the population that you don't get to study because you can't count it, the average of the population, which we call mu, yes, which we call mu, is going to be this, the sample drawn, if you will, times the population percentage. You don't know that, of course. That's what you're trying to estimate, is that guy right there, but you don't know what he is. The standard deviation around that, little sigma, is going to be n times p times q square rooted. And again, don't memorize that. It's not worth memorizing. Back in 243, we very often just used technology to calculate these numbers. And we were happy with that, and I was happy with that. But here's the deal. This is the population. You're trying to estimate via a sample based on the wonderful binomial distribution. Now you have to make the limitation go along with that. Now the population does have a probability associated with it, little p, but you don't know what it is. So what you do is you look at this formula and you go, God, it's a gorgeous formula. If I just knew what little p was, I would know what mu was, but you don't. So, oh, go ahead, Alan, go ahead.
What is mu again?
Mu is the population average. So if you want to think of it this way, it's the average number of times we should get heads on, say, 10 spins of a coin. Does that make sense? If it were 50%, 10 times 50% is 5. Done. So it would be the average number. So what we're going to do is, I'm going to look at this formula right here. Can you see how this formula relates to the sample proportion down here? Now, p hat is the sample proportion. See how that's tied to the population proportion. The sample proportion is what you get from your data. The sample proportion is out there floating around somewhere in space. You don't know what it is, though. Can you see how this formula could technically be rewritten to look kind of like this one? A little bit of mathematics. If you multiply both sides by n, you get n times p hat equals x. Number of heads equals proportion of heads times number of trials. Number of heads equals proportion of heads times number of trials. It's the same equation, it's just solved for the other variable. You divided both sides by n to get it that way. Is that believable? Is it fair? I want to make sure it's fair. It's the same equation, but what we've done is we've removed the parameter values and replaced them with sample values to make it proper sampling. Is that fair? Now this part will not be as fair for you mathematically. I'm not going to walk you through the mathematics in class because I piss people off when I do that. I did make a video, though, that gets you from this formula down to this one. There is a mathematical, very, very clever, I shouldn't say clever, a very, very factual mathematical algebraic way to get the standard deviation of the population knocked down to what's called the standard error of the sampling distribution. So Ali, back to your question about sample versus population. The standard error is the plus or minus on your sampling distribution, whereas this is the plus or minus on your population distribution. So this is what you'll never know, because it's in the population, it's floating out there. This is in the sample, which is what you are going to know. So if you want to know why this comes from this, I've got a video linked off the resources page. You can click on that. It's like a 3-minute video. I think I walk you through it on a chalkboard, how to get it. If you're interested in the math, I can also show you after class if you want to see it now. I'm not going to do it in class, though. It pisses people off. Now, that's one standard error or one standard deviation. Think of it as a standard deviation of the sample, but just it's called standard error in the biz for whatever reason. What percentage of data is contained within one standard deviation? Do you remember?
64.
Ho! Ish, somewhere in there. I'd say roughly 2/3. Roughly 2/3. How about 2 standard deviations? 95. How about 3 standard deviations? Yeah, we're getting up there now, right? 90, almost 100%. We're getting almost 100% within 90. How about 4? How about 5? How about 6?
All the time? That's all.
As long as you have bell curve, right? As long as you have, but don't we automatically get a bell curve because of the central limit theorem? You don't remember that, that's okay. That's what the review quiz is about if you want to do it. We automatically get a bell curve as soon as you start sampling because the central limit theorem says we are going to, as long as you sample independently. So, the bell curve is there, which means we now have the standard deviation, and we can go out. Now this, the formatting's terrible, hang on. That should be all subscript, I don't know why it's not. Hang on, let me fix it. Critical. Sorry about that, subscript. There we go. Save that. There we go. So, that's one standard error right there. By multiplying it by a value, 1, 2, 3, you pick up more percentage. So if you leave it at 1, the standard error itself is 68%. If you use 2, 1.96 or 2, it becomes 95%. What do those numbers mean? That's tied to how confident your interval is. That percentage that is tied into this value right here is how confident your interval is. I want to revisit that idea as we go through today. Which one do you hear very often in the news or in your research as you're studying? Well, maybe you haven't seen them yet. Everybody read Gallup-Poll? You don't read them for fun like I do. When you do your research for your psych classes and your social classes and your natural resources classes? No, not yet? What's the most common confidence you read about when you're reading those? Go ahead. Yeah, 5% p-value, which 95% confidence. Yeah, 95 is the most common level of confidence. I have a little chart in this spreadsheet for you, should you ever need it. 95% confidence, which is how much area is trapped under the curve, is tied into 2 standard errors. It's technically 1.96. Everybody calls it 2 because that's a good enough working definition. If you only go with 1, that's 68%, like we just said. If you want to go to 1.645, that's 90% confidence. You see what's happening? It goes back to Chris's point. As we get more confident, we're pushing further out, making the interval wider, which would make the margin of error wider. Go ahead, Rory. Ask me that question.
Is there like a guideline somewhere that's like scientific polls have to be more confident than like social polls or anything like that?
Not that I know of, and as a matter of fact, the fact that 95% is used is based kind of on an archaic, arbitrary article written in like 1860. But it is used. But I'm going to show you guys throughout this class why you might not always want to use 95%. I'm going to show you how to think outside of that 150-year-old because we've always done it box. You know, but correct in thinking that there is a common confidence. It's usually that guy right there. It's usually that guy right there. Now, when you talk about a confidence interval, the confidence part comes from this number. You pick the confidence before you form it, and then you use this number to calculate the interval. So I'm going to back up one more slide, and we're going to apply this to our data here in a second. We're going to apply it to our data in a second. So, standard error. Can we calculate this right now based off our data? Based off the data we got in class yesterday. Do we know what p-hat is? We do. It's 41.5%, right? Do we know what little n is? It's 270. Do we know what q-hat is? You might not know what it is yet, but you do know what it is numerically.
It's the other half.
It's the other half. If p-hat is the proportion of heads, Q hat's the proportion of? Tails. It's the other, now you don't actually, and some books actually write that as 1 minus P hat, as opposed to Q hat, which is, I think it's a little more cumbersome, but it's actually a little simpler because it's one less variable. But yeah, if it's binomial, if you know this is 41.5%, you know that is 59.5%, if 58.5%, thank you. I can't add or subtract. I can usually multiply either. Which is why I can't do this crap in my head. But that's okay, we don't have to do it in our head. We can do it with technology. So we can calculate this, right? We can get a value for this. Then all we've got to do is decide how confident we want to be in our results. I vote for 95% for starters. We can always adjust it later, and I think we should adjust it later, and we will adjust it as we go through the class. But let's just start with standard operating procedure, 95%. If that's okay with you, Rory, and everybody else. So in other words, we have to pick our critical. It's called a critical value because, it's a bit of an antiquated term. It's where you decide to slap your lines. It's where you decide to slap your lines to trap your area underneath. So it's the critical cutoff point. So we'll go ahead and use 1.96 or 2. We might use 2. Let's use 2. We're getting the technology being more exact. Cool? Let's crunch some numbers. Let's turn this off. And let's get into our penny spins. All right. Let's turn the light on. It's kind of dark. Any questions you guys have before we get into this right now? Anything kind of like this? Okay, everything you said is okay except for like this thing right here.